This is Jack Jackson. In this video we're going to look at exponential functions, and second only to linear functions, exponential are one of the most important classes of functions that we could look at. Linear functions are probably the most important, exponentials are probably the next most important. And in fact we can develop many of the ideas about exponential functions and many of their characteristics we can see as similar to linear functions but ramped up one level higher in the order of operations. So let's see if I can explain this or show this. So the formula for a linear function is y equals mx plus b, or maybe f of x equals mx plus f sub 0. So f sub 0 is the y-coordinate of the y-intercept. And so notice how this basically works in a table is if you're starting with the value 0 f sub 0, every time you add 1 to x, you're adding m to y. So x counts how many times we repeatedly added m, and so repeated addition then becomes multiplication. So we're taking the original f sub 0, adding to that x's, or m, x times. Well, over here in the exponential, what we're doing is we start at the point 0 f sub 0. So this f sub 0 is the y-coordinate of the y-intercept. Notice that works out. If you plug in 0 here, you get b to the 0 is 1 times f sub 0 is f sub 0. And then notice when x is 1, we're multiplying by b. When x is 2, we're multiplying by b again. So over here, we're starting with f sub 0, we're adding to it. Over here, we're starting with f sub 0, and we're multiplying by it. Multiplication's one level higher than addition. Here, we're repeatedly adding this slope m. Here, we're repeatedly multiplying by this base b. And I have a tendency to try to use these letters b for the base. Some people will use r for common ratio, but I reserve r for something else here. So we use b for base, and so we're repeatedly multiplying. Well, how many times do we repeatedly adding is called multiplication, so this becomes multiplication here. Repeated multiplication becomes powers, so this is an exponent or power right here. Okay, we may come back with some other similarities in a minute. So it turns out that this base is a constant if it's an exponential function, just like the slope is a constant over here if we're doing linear functions. Now, another way to see these is the base is 1 plus r, where r is a percentage rate of growth. So exponential functions are functions which have a constant percentage growth. Linear functions have a constant rate of growth. So, for example, something is going up, say, by $500 a year, that would be linear growth. Linear function. Something that's going up by 5% each year, that would be exponential growth. You can convert from a base b to any other base that you want, actually, but a base from base b we convert to our standard base of e if we change this x to be some constant times x. And so this constant is like a percentage rate of change, but it's a percentage rate of change compounded continuously. Okay, so the r is a periodic percentage rate of change, the k is a continuous rate of change. There's basically two shapes, concave up with a positive range either way. It has an asymptote on the far left or the far right, but not both. And it increases when the base is bigger than 1 and decreases when the base is less than 1. We'll look at that a little bit more in a minute. Now what happens in the table? Well, if you remember in the table over here on the linear function, adding equal amounts to x, or equal changes in x result in equal changes in y. So if the x's are evenly spaced, we're adding a constant each time to find the next y. In the table over here on exponentials, if the x's are evenly spaced, we multiply by a constant number each time to find the next y. In fact, over here, if the x's are going up by 1, this constant that we're adding each time is the slope. That's the m right here. Over here on the exponential side, if the x's are going up by 1, we're adding 1 to the x's each time, then the y's will be multiplied by a constant, and that constant is the base b. Now, what do you do over here if the base, if it's not going up by 1, how do you find m? Of course, if it's going up by 1, this common difference is the slope m. But if it's, so delta y is just m when delta x is 1. Well, you adjust it by dividing by delta x, to get a rate of change here, vertical change divided by horizontal change, a ratio of changes, to find the slope. And of course, that's constant between any 2 points. Okay? Well, over here, you would find the base that you're multiplying by. It would be this common ratio, y2 divided by y1, if delta x is 1. How do you adjust? You adjust by raising to the 1 over delta x power, in other words, the delta x root. Again, we're one level higher in the order of operations. Here you subtract y's to find the base when the delta x is 1. Here you divide y's to get the base when the delta x is 1. So delta x is 1. The slope is just the difference in y's, and delta x is 1. The base is just the ratio of the y's for linear and exponential respectively. When delta x is not 1, you can take any 2 points in your table or on your graph and do delta y divided by delta x. The difference in y is divided by the difference in x is to find the slope here. To find the base here, you divide the 2 y's, but then you take the delta x root. A root is one level higher than a division. Division is one level higher than the subtraction in the order of operations. So adding 1 to x results in adding m to y recursively over here on the linear, and so adding 1 to x is multiplying by y in the recursive form over here for the exponential. Okay, and I think I already said this part here. Moving to the right one on the graph moves the y values up vertically m units from any point on the graph. On the linear, moving the right one on the graph multiplies the y values by b from any point on the graph. Linear functions have a constant rate of change and constant slope. That is the most important thing you should remember about them. And the most important thing you should remember about exponential functions is they have a constant relative rate of change. That is a constant percentage change. This periodic rate is represented by r. K is the continuous relative rate of change. And the relationship between the k and the r and the b up here, I think you can see the b equals 1 plus r. And b to the x, or b is e to the k. So b equals e to the k. Another way to say that is k is the natural logarithm of b, and b is 1 plus r. So that's the relationship. Of course, r is b minus 1. Now, if you restrict the domain to only be natural numbers, then we call a linear function an arithmetic sequence, and this gives you a recursive formula and a non-recursive formula for sequence, and then the sum of the sequence is an arithmetic series, and there's a shorthand for that. Short formula, closed form for formula. If you take an exponential function and restrict it to the natural number domain, it's called the geometric sequence. So geometric growth, exponential growth, same thing basically. Arithmetic growth, linear growth, that's the same thing. Here's a formula for recursively formula and a non-recursive formula for that, and then here's the formula for the sum. And in the case of an exponential or geometric sequence, you can actually add up infinitely many of these things and get a finite number. I'm not going to go over the formula right now, but if you'll look here, zoom in a bit. If you'll look here at the formulas, I think you can see something. If you'll buy this and believe this formula right here, which I actually prove in some of my algebra videos, then you can look at what happens when you take the limit as n goes to infinity. So this formula right here is for adding up the first n things, a finite number, like add up the first 2 or 3 or 50 or 100 terms. Okay, you get this right here. But now if we want to find what happens when you add infinitely many things, it's going to be a limit of this sequence of partial sums. So it's going to be take this formula and take the limit as n goes to infinity. Well, you see if b is a absolute value is bigger than 1, then this thing is going to go off to infinity or minus infinity. But if absolute value of b is between 0 and 1, between 0 and 1, absolute value of b is less than 1. So b is between -1 and +1, not including 1 or -1. Then this term right here will go to 0. And so the formula for an infinite sum becomes this right here. So there's an example of where we can apply a limit concept to make sense of adding up infinitely many things and yet getting a finite number. So let's look a little bit more at exponential functions. Again, they're second only to linear functions in importance and application. Exponential functions are those with a constant percentage rate of change, that is, a constant relative rate of change. Exponential functions have the domain of all real numbers and are continuous functions. Okay, and we can take, here are the three forms here, and in these three forms, if the b is bigger than 1, the r will be positive and the k will be positive, and we'll have exponential growth, increasing concave up, horizontal asymptote of 0 on the right, increasing going towards infinity on the horizontal asymptote on the left, increasing going towards infinity on the right, so increasing concave up the whole way. And it's increasing kind of slow at first, and then it picks up speed and gets very, very, very fast later on. Exponential decay looks like this, the same formula, but the base is less than 1, or the r, and that happens exactly when the r and the k both are negative. And this will look like this, so it has the horizontal asymptote of the x-axis on the right, of 0, and the limit as x goes to negative infinity is positive infinity. So this is decreasing concave up the whole way. So exponential growth is increasing, exponential decay is decreasing. The only other really possibility you would have is a base equal to 1. And a base equal to 1 really is not an exponential function because that's just really just a constant function. So we don't really count that as an exponential. And we're not going to try to see what might happen if we try to let a negative base, because it would be full of all kinds of holes and stuff, because there's a lot of places when you take a negative to some powers that are undefined. And so that would be a strange function. It would have a lot of discontinuities in it. So we're not going to examine that one. And so those are the basic things. Let's continue on with this just a little bit and talk about logarithmic functions as well. Logarithms are just inverses of exponential functions. So the most basic exponential function, say, is g of x equals b to the x, right here. And so that means g inverse is log base b of x. So in other words, if you write y equals log base b of x, that's just another way of writing b to the b to the y power equals x. All right. So y is the logarithm. The word logarithm is actually synonymous with the words exponent or power. So y is the logarithm, y is the power when we rewrite it this way. So these are the same equation. One is solved for x and one is solved for y. Just like if you said y equals x plus 2, or you said x equals y minus 2, those are exactly the same order pairs. Make both of those equations true. There's basically the same relationship. It's just one version of the equation has it solved for x and the other one says solved for y. Same thing is going on here. Now we've already shown that inverses of continuous functions are continuous, and since exponential functions are continuous everywhere, they're defined. A logarithm is an inverse of an exponential. We know that a logarithm is continuous everywhere. It's defined as well. Basic exponential functions like these up here, just b to the x equals y, those have domain all reals and range the positives. So a basic logarithm, like y equals log base b of x, is going to have a domain the positives and a range reals. So that is one connected interval, so logarithms are actually continuous functions. Okay, and let's take a look at some characteristics. So right now I'm just going to restrict myself to basic y equals b to the x, where the base is bigger than 1. Of course, that'll be r and k are positive. So if we look at f of x as b to the x, like y equals 2 to the x or y equals e to the x, the domain is all reals, the range is positives, they're increasing concave up. Since it's increasing, that makes it 1 to 1. As a horizontal asymptote is y equals 0 on the left, so you take the limit of this as x goes to negative infinity, and you get 0. Limit as x goes to positive infinity is infinity. 0, 1 is this particular point on there, the y-intercept. It doesn't have an x-intercept, and so here it looks like this. This is 2 to the x. So notice it has 0, 1, 1, 2, 2, 4, 3, 8, negative 1 1/2. And the inverse function will have all those ordered pairs reversed. So instead of 0, 1, it has 1, 0. Instead of 1, 2, it has 2, 1. It also has 4, 2 instead of 2, 4. Instead of 3, 8, it has 8, 3. Instead of negative 1 half 1, negative 1, 1 half, it has 1 half, negative 1, and so forth. Instead of y equals 0 as a horizontal asymptote, it has x equals 0 as a vertical asymptote. In general, when you have inverse functions, they're reflections of each other about the line y equals x as far as the graphs go. So you see that this graph here is reflected over that line and gives you this one here. And so just because the original one's one connected piece, so is this one here, it's continuous as well. However, notice it's only defined for positives, so we don't take the logarithm of 0 or a negative. One more that's related to this, logistics functions. Okay, logistics functions are functions a over 1 plus c times e to the minus kt, where k, c, and a are constants. We're going to let k and c be positive. A could be positive or negative, actually. Usually we think of it as positive. And so what happens here, exponential functions have a constant percentage growth. That models a lot of things, like if you have a biological population, for example, and it has unlimited resources, it will have a tendency to grow at a certain percentage rate, and that would be exponential growth. But if you took a biological population and gave it limited resources, like bacteria in a culture where you're only going to feed it so much, and only has so much room, then what happens, it starts out and looks very similar to exponential growth, but then it sort of reaches a point of what we call point of diminishing returns, where we have an inflection point, and it starts to grow, continue to grow, but grow concave down, and eventually it levels off to some limiting value here. So notice that this one, if you take the limit as x goes to infinity, let's see what happens. K is a positive, so k times t is a negative number that's getting larger and larger in absolute value, and e to that power, of course, is going to go to 0. So this goes to 0, and you get a over 1 is a. So this limit right up here is the a value. In this particular example, it's 1,000. However, you take the limit as x goes to negative infinity, this part, of course, you get the limit of all of these over each other. What happens here is this part right here becomes a positive power that's larger and larger and larger. So the denominator gets larger and larger and larger, whereas the numerator is staying a fixed constant. That's our form, a constant over infinity. We know that limit is going to go towards 0. And so that always has an asymptote here. Notice in particular, this is a continuous function, but the denominator is never 0. It's built up out of ratios of built up out of the pieces of continuous functions that we've looked at before, right? It's a ratio. It's the quotients, the limit of the quotients, quotient limits, provided they both exist, and so forth. And we see that this, in fact, is continuous. But notice it has horizontal asymptotes on the left and right, but they're not the same. Rational functions, for example, if they have a horizontal asymptote, it's the same on the left and right. But here's an example where you have horizontal asymptotes on both left and right, but they're not the same. Okay, let's stop there for this video.